Somewhere in the constellation Hercules, 1,200 light-years from Earth, there is a planet more than twice the width of Jupiter. You would expect something that enormous to be a crushing monster, a world of unimaginable gravitational force. It is not. HAT P67b weighs less than half of Jupiter. Its density is lower than a marshmallow. Recent observations confirmed its atmosphere is bleeding into space at 10 million tons per second, streaming ahead of it in a ghostly tail of helium, stretching more than 130 times the planet's own radius. Within a few 100 million years, it will be swallowed by its own dying star. This is not the largest planet in the way you imagined. This is a planet so impossibly inflated that the word planet barely applies. If you enjoy journeys that shatter your assumptions about what the universe can build, consider tapping that like button and subscribing. It means more than you know, and it keeps stories like this one coming. Now, settle in, get yourself comfortable. Let's begin. Close your eyes and imagine the largest planet in the universe. Whatever your mind builds, it is wrong. But the mistake you make reveals something important about how humans think about size, about power, and about what a planet is supposed to be. So let us start with what you probably imagined. You pictured something enormous, something heavy, something with gravity so ferocious it could crush spacecraft and swallow moons. You imagined a scaled-up version of the biggest planet you already know. You imagined a bigger Jupiter. That instinct makes perfect sense. Jupiter is the king of our solar system, and everything about it screams dominance. It is 11 times wider than Earth. You could line up more than 1,300 Earths inside its volume and still have room left over. Its mass is 318 times that of our planet. It weighs more than every other planet, moon, asteroid, and comet in the solar system combined, and then doubles that figure for good measure. Jupiter is not just the biggest thing orbiting our sun. It is the gravitational anchor that shaped the architecture of every world around it. Stand on the cloud tops of Jupiter, if you could survive, and you would weigh 2.5 times what you weigh on Earth. The atmospheric pressure below those clouds climbs to levels that would flatten a nuclear submarine in seconds. Winds scream at 350 miles per hour. The Great Red Spot, a storm that has been raging for centuries, is so large that Earth could fit inside it with room to spare. Lightning bolts in Jupiter's atmosphere release energies 1,000 times greater than those on Earth. Radiation belts surrounding the planet are so intense they would deliver a lethal dose to an unshielded human in minutes. This is a world of overwhelming force. Jupiter's gravitational reach extends so far that it has captured 95 known moons, some of them large enough to qualify as worlds in their own right. Ganymede, its biggest satellite, is larger than the planet Mercury. Europa, hidden beneath a shell of ice, harbours a global ocean that may contain more liquid water than all of Earth's oceans combined. Io, pulled and squeezed by tidal forces, erupts with volcanic fury unlike anything else in the solar system. Jupiter is also a cosmic guardian. Its massive gravity deflects comets and asteroids that might otherwise pummel the inner solar system. Without Jupiter, Earth would be struck by large impactors far more frequently. Some scientists believe that the existence of a gas giant in the outer solar system is one of the reasons complex life had enough stable time to evolve on our planet. Jupiter does not just dominate our solar system. It may have helped make life possible. Now here is where human intuition kicks in with a very specific expectation. If Jupiter is this powerful at 11 times the width of Earth and 318 times its mass, then the largest planet in the universe should be all of this multiplied. It should be wider, heavier, denser, fiercer. It should be Jupiter on steroids. The storms should be more violent. The gravity should be more crushing. The radiation should be more lethal. The moons should be more numerous. Everything about the largest planet should represent the absolute extreme of what planetary physics can produce. This expectation is not random. It follows a pattern humans observe everywhere in nature. The largest elephants are heavier than smaller elephants. The tallest skyscrapers contain more steel than shorter ones. The biggest stars are more massive than average stars. When things get bigger, they usually get heavier and more powerful. Mass scales with volume, strength scales with mass. This relationship holds across nearly every domain of human experience. For centuries, this pattern held firm in planetary science as well. Astronomers knew of 9 planets, then 8 after Pluto's reclassification. The relationship was straightforward. The rocky inner planets were small and dense. Earth, the largest of them, measured roughly 8,000 miles across with a density of 5.5 grams per cubic centimetre. The gas and ice giants of the outer solar system were large and comparatively less dense, but still impressively massive. Jupiter sat at the top of the hierarchy. Biggest, heaviest, most gravitationally powerful. The correlation between size and mass seemed reliable. It seemed like a law of nature. Then astronomers started finding planets around other stars. And the pattern shattered. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995, 51 Pegasi b, detected by Michel Mayor and Didier Queloz using radial velocity measurements at the Observatoire de Haute-Provence. The discovery shocked the astronomical community for a reason that seems almost quaint now. 51 Pegasi b was a gas giant roughly half the mass of Jupiter, but it orbited its star in just 4.2 days. That placed it closer to its star than Mercury is to our Sun. Nobody expected to find a Jupiter-sized world in such a scorching orbit. The prevailing models of planet formation said gas giants should form far from their parent stars, in the cold outer reaches of planetary systems where volatile ices could accumulate into massive cores. Finding one practically touching its star was like finding a snowman standing in a blast furnace. The discovery opened the floodgates. Within a few years, astronomers found dozens of similar planets. Giant worlds on tight orbits with searing surface temperatures. They earned a nickname that stuck: hot Jupiters. These planets immediately revealed that the relationship between size and mass was more complicated than anyone assumed. Some hot Jupiters were heavier than Jupiter, but roughly the same width. Others were lighter than Jupiter, but noticeably wider. A few were significantly wider than Jupiter while being only a fraction of its mass. The neat correlation that worked so well in our solar system was not a universal law. It was a local coincidence. As detection methods improved, the exoplanet catalogue exploded. Transit photometry, where astronomers watch for the tiny dimming of a star as a planet crosses in front of it, allowed precise measurements of planetary radii. Radial velocity observations, tracking the wobble a planet induces in its host star, provided mass estimates. Combining these two techniques gave astronomers something revolutionary: density measurements for distant worlds. And the densities were strange. Some gas giants had densities comparable to Jupiter, roughly 1.3 grams per cubic centimetre. Others had densities far lower, below 1 gram per cubic centimetre below the density of water. A few registered densities so low they seemed physically unreasonable. Planets with the volume of Jupiter but less mass than Saturn. Worlds with the width of a giant planet but the substance of something closer to heated fog. These were the inflated hot Jupiters. Planets puffed up to sizes that their mass alone could not explain. Standard models of planetary structure predict that a gas giant of a given mass and age should contract to a specific radius as it cools over time. The models work well for cold gas giants far from their stars, but for planets on tight orbits, bathed in intense stellar radiation, the models consistently underpredicted the observed radii. The planets were too big, not by a little, by 20, 30, sometimes 50% or more. The inflation problem became one of the central puzzles of exoplanet science. What was making these worlds swell beyond their predicted sizes? Where was the extra energy coming from? Why did some hot Jupiters inflate dramatically while others on similar orbits remained compact? The questions multiplied faster than the answers. Several mechanisms were proposed. Ohmic dissipation, where electrical currents generated by atmospheric winds moving through a planet's magnetic field deposit heat into the interior. Tidal heating, where gravitational interactions between the planet and its star flex the planet's interior and generate friction. Advective transport of heat, where atmospheric circulation patterns carry energy from the irradiated day side deep into the planet's interior, preventing it from cooling efficiently. Enhanced atmospheric opacity, where certain chemical compositions trap heat more effectively than standard models assume. Each mechanism explained some observations but failed to account for the full range of inflated radii seen across the population. What became clear, even as the details remained debated, was that proximity to a star fundamentally changes what a gas giant can be. A gas giant in the cold outer reaches of a planetary system behaves the way textbooks describe. It forms, it cools, it contracts to a predictable size determined by its mass and composition. It sits there, stable, for billions of years. But move that same planet close to its star, within a few stellar radii, and everything changes. The intense irradiation pumps energy into the atmosphere. That energy penetrates inward through mechanisms that are still being untangled. The planet swells, its density drops. Its structure becomes something Jupiter would not recognize. This is the critical insight that most people miss when they hear the phrase largest planet. The word largest, when applied to planets, carries an unspoken assumption. We assume it means the most massive, the most gravitationally powerful, the most physically impressive in every dimension. We assume that the largest planet is also the heaviest planet, that it must be a super Jupiter, a world that makes our own gas giant look modest. But radius and mass are not the same measurement. They do not tell the same story. A planet can have an enormous radius while carrying a surprisingly modest mass. This happens when something prevents the planet from contracting, when energy is deposited into its interior faster than the planet can radiate it away. The result is a world that is vast in volume but thin in substance. A cosmic balloon rather than a cosmic cannonball. The search for the largest exoplanet, therefore, becomes a more nuanced question than it first appears. Are we looking for the most massive planet? The one with the most material? That search leads in one direction, toward worlds many times the mass of Jupiter, heavy and dense and gravitationally terrifying. Or are we looking for the widest planet? The one with the largest radius? That search leads in an entirely different direction, toward inflated worlds, where the ratio of size to substance reaches extremes that challenge our understanding of what a planet can be. The distinction matters because it determines what the answer actually tells us. The most massive planets are impressive, but not particularly surprising. They are simply more of the same. More gas, more gravity, more pressure. The physics scales predictably. But the widest planets, the most inflated ones, are genuinely strange. Their size does not come from accumulating more material. It comes from their material being stretched, heated, and puffed into configurations that no cold planet could ever achieve. They are products of violence, of proximity, of extreme stellar environments reshaping what should be a straightforward ball of hydrogen and helium into something alien. As of today, astronomers have confirmed more than 5,700 exoplanets. The catalogue spans an astonishing range. Rocky worlds smaller than Earth, super-Earths with no analogue in our solar system, mini-Neptunes shrouded in thick atmospheres, ice giants, gas giants, worlds that orbit two stars simultaneously, planets that orbit so close to their stars that their surfaces drip with molten iron rain, planets that orbit so far from any star that they drift through interstellar space in permanent darkness. The diversity is staggering. Within this catalogue, astronomers have identified a handful of planets that occupy the extreme end of the radius distribution. These are the largest known worlds, not the heaviest, but the widest, and they cluster in a very specific category. They are almost all hot or highly irradiated gas giants on tight orbits. They are almost all inflated well beyond what their mass would predict, and several of them are not even as heavy as Jupiter. That last fact deserves to be repeated because it is the one that breaks most people's intuition. Several of the largest radius planets known to science are lighter than Jupiter. Some are significantly lighter. They are enormous not because they contain vast quantities of material, but but because the material they do contain has been stretched into a volume far exceeding what physics would normally allow for that amount of gas. They are cosmic cotton candy, vast, diffuse, and structurally precarious. Among all of these, one planet stands out. One world that sits at the very top of the radius chart in the NASA Exoplanet Archive, occupying a region of the mass radius diagram so extreme that almost nothing else survives there. One planet that is not the heaviest, not the densest, not the most gravitationally ferocious world in the catalogue, but is one of the most physically swollen, most absurdly oversized, most structurally fragile objects that has ever earned the title of planet. Its name is HAT P67b. It orbits a dying star in the constellation Hercules, 1,200 light-years from Earth. It was discovered by the Hungarian Automated Telescope Network, using small wide-field telescopes at two observatories, the Fred Lawrence Whipple Observatory in Arizona and the Mauna Kea Observatory in Hawaii. Observations were first made in 2005 and 2008. Follow-up photometry captured its transits in 2011 through 2013. Its confirmation and characterization paper was published in 2017, and when astronomers looked at the numbers, they found something that did not make sense. HAT P67b has a radius of approximately 2.14 Jupiter radii. Let that figure register for a moment. This planet is more than twice as wide as Jupiter. If you placed it next to Jupiter, it would dwarf the king of our solar system the way Jupiter dwarfs Earth. Its volume is roughly 10 times that of Jupiter. If our solar system's biggest planet is a basketball, HAT P67b is a beach ball sitting next to it. By any standard of size, this is one of the largest planets ever confirmed. The NASA Exoplanet Archive lists it among the very largest radius exoplanets known. In terms of sheer physical width, it is a world that makes Jupiter look ordinary. But here is where the story turns. Here is where everything you assumed about what the largest planet should be collapses. HAT P67b is more than twice the width of Jupiter, but it is not twice the mass. It is not even the same mass. The most recent measurement, published in 2025 by a team using the NEID spectrograph on the WIYN 3.5 meter telescope, found a mass of approximately 0.45 Jupiter masses, less than half the mass of Jupiter, roughly 1.5 times the mass of Saturn, yet more than twice Saturn's width. Read those two numbers together and let them sink in. A planet more than twice as wide as Jupiter, weighing less than half as much. That combination produces a density so low it sounds like a mistake. Approximately 0.061 grams per cubic centimeter. To understand how absurd that number is, consider this. Water has a density of 1 gram per cubic centimeter. Jupiter has a density of about 1.33 grams per cubic centimeter. Saturn, the least dense planet in our solar system, still manages 0.69 grams per cubic centimeter. A marshmallow has a density of roughly 0.1 to 0.15 grams per cubic centimeter, depending on the brand. HAT P67b is less dense than a marshmallow. This is not what the largest planet was supposed to be. This is not the crusher, the dominator, the gravitational tyrant that human intuition demands. This is something else entirely. This is a planet so inflated, so stretched, so grotesquely oversized for its mass that it barely holds together. A world made more of nothing than of something. A gas giant in which the word giant refers only to dimensions, not to substance. And it gets worse. Because HAT P67b is not sitting safely in the cold outer reaches of a distant solar system, quietly being strange. It is in one of the most violent environments a planet can occupy. It orbits its host star at a distance of only 0.065 astronomical units. That is roughly 10 million kilometers. For comparison, Mercury orbits our Sun at about 58 million kilometers. HAT P67b is almost 6 times closer to its star than Mercury is to ours. Its orbital period is only 4 days and 19 hours. While Earth takes a year to complete one lap around the Sun, this planet screams around its star 76 times in the same period. The host star itself is not a quiet, stable companion. HAT P67 is an F-type subgiant star, roughly 1.73 times the mass of our Sun and 2.65 times its width. It is a star that has begun to evolve off the main sequence, swelling as it exhausts the hydrogen fuel in its core. It spins rapidly, with a projected rotational velocity of nearly 36 kilometers per second. It is roughly 12 times more luminous than our Sun, and it is getting brighter as it ages. This means the planet is being cooked. Its equilibrium temperature is approximately 1900 Kelvin, placing it right at the boundary between the categories astronomers call hot and ultra-hot gas giants. At these temperatures, molecules in the atmosphere begin to break apart. Chemistry becomes dominated by atoms and ions rather than the familiar molecular species found in cooler atmospheres. The day side of this planet glows with heat, and the planet is responding to this onslaught in the most dramatic way possible. It is falling apart. But that story, the story of a planet hemorrhaging its own atmosphere into space, trailing a ghostly tail of helium across millions of kilometers of empty vacuum, comes next. For now, sit with the paradox. The largest planet known by radius is not a larger version of Jupiter. It is not heavier. It is not denser. It is not more gravitationally powerful. It is the opposite of everything you expected. A world of staggering dimensions built from shockingly little mass. A planet that is enormous specifically because it is inflated, swollen, puffed beyond reason by forces that have nothing to do with accumulating more material and everything to do with being in the wrong place at the wrong time. The largest planet is not the strongest planet, and that simple inversion is where the real terror begins. What comes next reveals exactly how this impossible object was found, why its measurements stunned the teams who studied it, and why a 2025 follow-up study declared that the planet is now on an irreversible path toward destruction. Finding HAT P67b was not a dramatic midnight revelation. It was a slow accumulation of data, spread across years, gathered by small telescopes that most people would walk past without a second glance. The instruments that discovered one of the most extreme planets in the known universe were not billion-dollar space observatories. They were modest, ground-based cameras with apertures of just 11 centimeters, roughly the diameter of a large coffee can lid. But they were patient. And patience, in exoplanet science, is everything. The Hungarian Automated Telescope Network, known as HATNet, operates a collection of these small, wide-field telescopes distributed across 2 sites. One set sits at the Fred Lawrence Whipple Observatory on Mount Hopkins in southern Arizona. The other watches from the summit of Mauna Kea in Hawaii. Together, they monitor hundreds of thousands of stars simultaneously, watching for the telltale dimming that occurs when a planet crosses in front of its host star as seen from Earth. This technique, called transit photometry, is conceptually simple. When a planet passes between its star and our line of sight, it blocks a tiny fraction of the starlight. The amount of dimming reveals the planet's size relative to the star. The timing of repeated dimmings reveals the orbital period. HATNet observed the star now designated HAT P67 beginning in 2005. Additional observations followed in 2008. The data showed periodic dips in brightness consistent with a large object transiting the star every 4.81 days. The depth of the transit suggested something enormous was passing in front of the stellar disk. Follow-up photometry using the larger 1.2-meter telescope at the Fred Lawrence Whipple Observatory captured a full transit on May 28, 2012, along with 5 partial transits observed between 2011 and 2013. The transit was real, repeatable, and deep, but confirming that the transiting object was actually a planet rather than something else entirely required a second line of evidence. In exoplanet science, transits alone are not proof. Several astrophysical scenarios can mimic a planetary transit signal. A faint background eclipsing binary star, blended with the light of the target star, can produce periodic dimmings that look identical to a planetary transit. A brown dwarf, an object too massive to be a planet but too small to sustain hydrogen fusion like a true star, can also transit and produce similar signals. Ruling out these false positives requires measuring the mass of the transiting object, and that is where HAT P67b became a problem. The standard method for measuring an exoplanet's mass is the radial velocity technique. As a planet orbits its star, its gravitational pull causes the star to wobble slightly. This wobble shifts the star's light toward bluer wavelengths when the star moves toward Earth and toward redder wavelengths when it moves away. By measuring these tiny spectral shifts over time, astronomers can determine the mass of the orbiting companion. The technique is extraordinarily precise. Modern spectrographs can detect stellar wobbles corresponding to velocities of less than 1 meter per second, slow enough that a person walking at a casual pace would outrun the signal. But the technique has a critical weakness. It requires clean, stable, spectral lines in the starlight. If the star itself is doing something that smears or distorts those lines, the planetary signal drowns in noise. HAT P67 is exactly that kind of difficult star. It is an F-type subgiant rotating at a projected velocity of nearly 36 kilometers per second. For context, our Sun rotates at about 2 kilometers per second. HAT P67 spins roughly 18 times faster. That rapid rotation broadens every spectral line in the star's spectrum, smearing them into wide, shallow features that make precise radial velocity measurements extraordinarily difficult. The subtle wobble induced by an orbiting planet of less than 1 Jupiter mass gets lost in the noise of the star's own rotational broadening. Early radial velocity observations taken at the Keck Observatory between 2009 and 2012 could not pin down a definitive mass. They could only establish an upper limit. The transiting object had a mass of less than 0.59 Jupiter masses. That ruled out a stellar companion or a massive brown dwarf, both of which would produce much larger wobbles, but it left the actual mass frustratingly uncertain. The planet could weigh anywhere from a small fraction of Jupiter's mass up to that upper limit. The difference between those possibilities was enormous in terms of what the planet actually was. The confirmation came through an alternative technique called Doppler tomography. Instead of trying to measure the star's overall radial velocity shift, Doppler tomography tracks how the planet's shadow moves across the spinning stellar disk during transit. As the planet crosses in front of the star, it blocks light from a specific portion of the rotating surface. Because different parts of the star are moving toward or away from us due to the rotation, the blocked light carries a specific velocity signature. By watching how that blocked velocity signature changes during the transit, astronomers can confirm that the dimming is caused by a compact object moving across the stellar disk, rather than by a blended background binary or an instrumental artifact. Two separate Doppler tomographic detections of the transit eliminated the eclipsing binary scenarios. The transiting object was confirmed as a genuine planetary companion. The observations also revealed that the planet's orbit is aligned with the spin of its host star to within roughly 12 degrees in projection. This alignment is a clue about the planet's history. It suggests that HAT P67b likely migrated inward to its current scorching orbit through interactions with the protoplanetary disk early in the system's history, rather than being scattered inward through violent gravitational encounters with other planets, which tend to produce tilted or even retrograde orbits. A later independent confirmation strengthened this conclusion. A team using the Galileo National Telescope detected the Rossiter-McLaughlin effect during a transit of HAT P67b. This effect is a subtle distortion in the star's radial velocity signal that occurs when a transiting planet blocks part of the rotating stellar surface, temporarily skewing the apparent velocity of the star. By measuring the shape and amplitude of this distortion, the team determined the projected spin-orbit angle to be just 2.2 degrees, plus or minus 0.4 degrees. That is an almost perfectly aligned orbit. The planet's orbital plane and the star's equatorial plane are nearly identical, as if the planet were still obediently following the track laid down by the protoplanetary disk from which it formed billions of years ago. This near-perfect alignment argues strongly against any violent dynamical history. No close encounters with other massive planets, no gravitational scattering events, no chaotic rearrangements. HAT P67b arrived at its current orbit gently, carried inward by the smooth, viscous drag of the disk itself. Whatever made this planet extreme, it was not a violent past. It was a violent present. The discovery paper, led by George Joe and colleagues, was published in 2017 in the Astronomical Journal. It reported a radius of approximately 2.085 Jupiter radii. It reported the mass upper limit of less than 0.59 Jupiter masses and a lower limit of greater than 0.056 Jupiter masses, based on limitations imposed by Roche lobe overflow. And it reported what those numbers implied. HAT P67b was among the lowest density gas giants known, a planet with the dimensions of a colossus and the substance of almost nothing. But the mass uncertainty was a problem. An upper limit is not a measurement. Saying the planet weighs less than 0.59 Jupiter masses is like saying a person weighs less than 200 pounds. They could weigh 190. They could weigh 80. The implications for the planet's density, structure, and evolutionary fate depend critically on the actual number. Without a precise mass, astronomers could not determine whether the planet's atmosphere was stable or actively escaping. They could not model its interior structure with confidence. They could not predict its future. For nearly 8 years, that mass uncertainty lingered. Various teams studied the planet's atmosphere, detecting extraordinary signatures we will explore shortly, but the fundamental question of how much this planet actually weighs remained open. The host star's rapid rotation continued to defeat conventional radial velocity campaigns. Then, in 2025, a team led by Gavin Wang published a breakthrough study. Using the NEID spectrograph, a next-generation instrument installed on the WIYN 3.5-meter telescope at Kitt Peak National Observatory, they conducted a radial velocity campaign specifically designed to overcome the challenges posed by the host star's activity. NEID achieves extraordinary spectral precision, and the team developed a sophisticated approach to separate the planet's signal from the stellar noise. They characterized the star's activity using photometry and spectral indicators, revealing that the star's rotation period of 5.40 days sits remarkably close to the planet's orbital period of 4.81 days. This near synchronization complicated the analysis further, because stellar activity signals at the rotation period can alias with the orbital period of the planet, creating false signals or masking real ones. To overcome this, the team employed a constrained quasi-periodic Gaussian process, a statistical method that models the correlated noise from stellar activity and separates it from the coherent signal of the orbiting planet. They jointly fit archival ground-based photometry, space-based photometry from the Transiting Exoplanet Survey satellite known as TESS, and their new NEID radial velocity observations. The result was the first robust mass measurement for HAT P67b, 0.45 Jupiter masses, plus or minus 0.15 Jupiter masses, combined with a refined radius measurement of 2.140 Jupiter radii, plus or minus 0.025. This yielded a density of 0.061 grams per cubic centimeter. That number, measured to roughly 33% precision, made HAT P67b the second lowest density hot giant planet known. Only one other world in the confirmed catalogue crosses below the threshold where planetary physics says objects should not survive for long. That threshold deserves careful explanation, because it is central to understanding why this planet is so scientifically unsettling. Research by Daniel Thorngren and collaborators has demonstrated that hot gas giants with densities below roughly 0.1 grams per cubic centimeter occupy a perilous zone. At these densities, the planet's gravitational hold on its own atmosphere becomes dangerously weak relative to the energy being pumped in by the host star. Extreme ultraviolet radiation from the star ionizes hydrogen and helium in the planet's upper atmosphere, heating it to temperatures where individual atoms gain enough energy to exceed the planet's escape velocity. The atmosphere starts leaking into space. For most planets, this process is gradual, a trickle of atoms escaping from the exosphere over billions of years. But for the lowest density hot giants, the math turns catastrophic. Below roughly 0.1 grams per cubic centimetre, the mass loss is no longer a gentle leak, it becomes runaway. The atmosphere escapes so rapidly that it cannot be replenished by the planet's remaining gas. The planet deflates, which reduces its gravity further, which accelerates the escape, which deflates it more. The feedback loop runs until the atmosphere is gone entirely, leaving behind either a stripped rocky core or nothing at all. Theoretical models predict that this runaway process should strip a planet completely within less than 100 million years. Here is the puzzle that haunted astronomers for years. HAT P67b has a density of 0.061 grams per cubic centimetre, well below the danger threshold. Its host star is not young. The system's age is estimated at more than 1 billion years. According to the runaway models, this planet should have lost its atmosphere hundreds of millions of years ago. It should not exist in its current form. It should be a bare core or a memory. Yet there it is, still enormous, still transiting, still puffy, still holding an atmosphere that by all theoretical predictions should have been stripped away long ago. The 2025 study resolved this paradox, and the answer involves the star itself. HAT P67 is not a stable main sequence star. It is a subgiant, a star that has begun to exhaust the hydrogen fuel in its core and is starting to evolve toward the red giant phase. During the main sequence lifetime of an F-type star, the ultraviolet radiation output follows a specific profile. Early in the star's life, when it is young and magnetically active, UV radiation is high. As it ages and its magnetic activity declines, the UV output drops. For most of its main sequence lifetime, HAT P67's ultraviolet flux was actually lower than what would be needed to drive runaway atmospheric escape from its planet. But now, as the star evolves off the main sequence and its luminosity climbs, the irradiation environment is changing rapidly. The extreme ultraviolet flux hitting the planet is increasing as the star swells and brightens. The Wang et al. Study concluded that the destructive atmospheric mass loss is a recent phenomenon. The planet survived for over 1 billion years in a state of relative stability, puffed up by the intense visible and infrared radiation from its host star, but not yet losing its atmosphere catastrophically. Only now, as the star enters its subgiant phase and its radiation profile shifts, has the atmospheric escape accelerated into the regime that theory predicts should destroy the planet. In other words, we are catching HAT P67b at a very specific and very brief moment in its existence. It has spent most of its life inflated but intact. Now it has entered the killing zone. The star is brightening. The atmosphere is hemorrhaging. The clock is running. The study estimated that the planet will be tidally disrupted or engulfed by its expanding host star within approximately 150 to 500 million years. To a human, that sounds like an eternity. In cosmic terms, it is a sliver. The universe is nearly 14 billion years old. 500 million years represents less than 4% of that total. This planet is in the final act of its existence, and we happen to be watching. To understand what this environment actually means for the planet, consider the physical conditions at its orbital distance of 10 million kilometers. The host star, already 2.65 times the width of our Sun, and 12 times more luminous, fills an enormous portion of the planet's sky. From the cloud tops of HAT P67b, assuming you could somehow hover there without being vaporized, the star would not look like the modest disk our Sun presents from Earth. It would dominate the heavens, stretching across roughly 20 degrees of sky, nearly 40 times the apparent width of our Sun as seen from Earth. The dayside hemisphere is drenched in radiation so intense that atmospheric molecules shatter into their component atoms. Sodium and potassium float as free atomic vapor. Hydrogen dissociates. Iron and magnesium may exist as gaseous species at these pressures and temperatures. The night side tells a different story. Tidally locked or nearly so, with the same face perpetually aimed at the star, the planet's far hemisphere receives no direct starlight. Temperatures there plunge by hundreds or potentially over 1,000 Kelvin, creating one of the most extreme temperature gradients in the known exoplanet population. Powerful atmospheric winds, predicted by general circulation models to reach speeds of several kilometers per second, attempt to redistribute this heat from day to night. These jet streams wrap around the planet at the equator, carrying scorching gas from the illuminated hemisphere toward the dark side. But the redistribution is imperfect. The night side remains substantially cooler. At the terminator, the razor-thin boundary between permanent day and permanent night, temperatures shift by hundreds of degrees across distances shorter than the width of a continent. Clouds may condense and dissolve in narrow bands along this twilight circle. This temperature contrast drives the atmospheric dynamics that are central to the inflation mechanisms we will explore next. The sheer intensity of radiation pounding the dayside has another consequence. It determines the equilibrium temperature of the planet, approximately 1900 Kelvin, which places HAT P67b right at a critical boundary in exoplanet classification. Below roughly 2000 Kelvin, most atmospheric chemistry is dominated by molecules, water vapor, carbon monoxide, methane. Above that threshold, thermal dissociation rips these molecules apart, and the atmosphere transitions to a regime dominated by free atoms and ions. HAT P67b straddles this boundary. Its dayside likely crosses into the atomic regime while its nightside preserves molecular species. The planet is not simply hot. It exists at the chemical tipping point, where the atmosphere transforms from one kind of object into another, depending on which hemisphere you observe. To appreciate how extreme HAT P67b truly is, it helps to visualize where it sits on the mass radius diagram, the fundamental chart that astronomers use to classify and understand the diversity of known planets. The diagram plots planetary mass on one axis and radius on the other. Every confirmed exoplanet with measured mass and radius occupies a point on this chart. The distribution tells a story. Most gas giants cluster in a predictable region. Planets near 1 Jupiter mass have radii near 1 to 1.2 Jupiter radii. As mass increases beyond Jupiter, the radius actually stops growing, and in some cases begins to shrink, because the increased gravity compresses the material more efficiently. This is a well-understood consequence of the physics of degenerate matter. Pile more hydrogen and helium onto a planet, and beyond a certain point, the added gravity squeezes the existing material into a smaller volume faster than the new material adds volume. The result is a maximum radius for cold gas giants of roughly 1 to 1.2 Jupiter radii, regardless of how massive they become. Hot Jupiters break this pattern. Intense irradiation inflates their radii above the cold planet maximum, scattering points upward on the diagram. Many hot Jupiters sit at 1.2 to 1.5 Jupiter radii. Some reach 1.7 or 1.8. A handful of extreme cases push past 2 Jupiter radii. HAT P67b sits in the uppermost corner of this diagram. A radius above 2 Jupiter radii at a mass below half a Jupiter. It occupies a region so sparsely populated that you can count its neighbours on one hand. The few worlds that share this extreme corner of the diagram are all intensely irradiated, all on short-period orbits, all losing mass, and they are all expected to vanish cosmically speaking in short order. The emptiness of that corner is not an absence of discovery. It is an absence of survivors. The mass radius diagram reveals something else that is crucial for understanding why this planet is so strange. For a given radius, there is a range of plausible masses depending on composition, temperature, and irradiation. A planet at 2 Jupiter radii could, in principle, be several Jupiter masses if composed primarily of hydrogen and helium and not excessively heated. It could also be less than 1 Jupiter mass if intensely inflated. But as the mass drops below roughly half a Jupiter mass while the radius stays above 2 Jupiter radii, the planet enters territory where standard interior models break down entirely. No combination of composition and equilibrium cooling produces that configuration. Something external must be actively pumping energy into the planet to prevent it from contracting. That something is the host star. The intense irradiation from HAT P67, now roughly 12 times the luminosity of our Sun and concentrated on a planet only 10 million kilometers away, deposits enough energy into the atmosphere to keep the planet bloated far beyond its natural equilibrium size. The precise mechanism by which this energy penetrates deep enough to affect the planet's overall radius remains an active area of research. But the observational fact is undeniable. This planet is vastly larger than any cold planet of similar mass could ever be. The system also holds another surprise that adds complexity to the picture. HAT P67 is not a single star. It is a binary system. Measurements from the Gaia spacecraft confirmed that a red dwarf companion star with about 0.58 solar masses and 0.68 solar radii orbits the primary F-type subgiant at a projected separation of roughly 3,400 astronomical units. That is an enormous distance, far too great for the companion to directly affect the planet's orbit or atmosphere today. But the presence of a binary companion raises questions about the system's dynamical history. Could gravitational perturbations from the distant companion have influenced the planet's migration inward to its current orbit billions of years ago? The planet's well-aligned orbit suggests smooth, disk-driven migration rather than chaotic scattering, but the full dynamical history of a binary system is always more complex than a single star system. The host star's rapid rotation adds yet another layer of intrigue. At nearly 36 kilometers per second, the star spins fast enough that its rotation period of approximately 5.4 days nearly matches the planet's orbital period of 4.81 days. This near synchronization could be coincidental, or it could reflect a physical interaction between star and planet. Tidal forces from a close-orbiting massive body can transfer angular momentum to the host star, gradually spinning it up or synchronizing its rotation with the planet's orbit. Some researchers have also proposed star-planet magnetic interactions as a mechanism that could link the two periods, though the evidence for such coupling remains circumstantial. What is not circumstantial is the planet's current state of crisis. Multiple independent observing campaigns have now confirmed that HAT P67b is actively disintegrating. The evidence comes from atmospheric transmission spectroscopy, a technique that analyzes starlight filtered through a transiting planet's atmosphere. As the planet crosses in front of its star, a thin ring of atmosphere along the planet's limb absorbs specific wavelengths of starlight corresponding to the chemical species present in the atmosphere. By comparing the stellar spectrum during transit to the spectrum outside transit, astronomers can identify which atoms and molecules populate the planet's upper atmosphere. For HAT P67b, these observations revealed far more than a list of chemical ingredients. They revealed a planet caught in the act of bleeding to death. A team led by Aaron Bello-Aruf used the Carmine spectrograph at the Calar Alto Observatory and detected sodium and ionized calcium in the planet's atmosphere. The ionized calcium detection was particularly striking. This species is typically found in significantly hotter planets. Its presence in HAT P67b's atmosphere suggests that the upper atmosphere is more highly ionized than standard models predicted. The data also revealed absorption in the hydrogen alpha and helium triplet lines, classic signatures of atmospheric gas escaping into space. A separate campaign led by Michael Gully Santiago used the Habitable Zone Planet Finder spectrograph on the Hobby Eberly telescope and found something even more dramatic. Over 13.8 hours of on-sky integration time, spread across 39 nights, the team sampled the entire orbit of the planet. They detected up to 10% excess absorption in the helium triplet line during transit, but the helium signal did not appear, only during the transit itself. Excess absorption appeared before the planet even crossed in front of the star, extending ahead of the planet by up to 130 planetary radii. 130 planetary radii. That is a tail of escaping gas stretching ahead of the planet in its orbit so far that if you could see it, the tail would dwarf the planet itself by more than 2 orders of magnitude. This leading tail structure is a direct consequence of the planet overfilling its Roche lobe, the teardrop-shaped region around the planet within which material is gravitationally bound to the planet rather than to the star. When the planet's atmosphere expands beyond the Roche lobe boundary, material spills over and falls toward the star. Because the overflowing gas is launched from the day side of the planet, which faces the star, and because orbital dynamics carry the gas forward along the orbit, the escaping material forms a stream that leads the planet rather than trailing behind it. The helium absorption showed Doppler velocity structures consistent with this picture. The gas was moving in the stellar rest frame, not the planetary rest frame, exactly as models of Roche lobe overflow predict. The Gully Santiago team also observed a significantly fainter trailing tail behind the planet, along with transit-to-transit variability in the helium line profile, consistent with the interaction of stellar and planetary winds. Using one-dimensional Parker wind models to estimate the mass loss rate, they found values on the order of 10 to the 13th grams per second, with large uncertainties owing to the unknown extreme ultraviolet flux of the F-type host star. Converting that to more intuitive units gives approximately 10 million metric tons of atmosphere escaping every single second. A third team, led by Cecilia and collaborators, analysed average spectra acquired after transits and found a clear helium absorption signal. They estimated that the planet's effective radius at the helium triplet wavelength corresponds to roughly 6 Jupiter radii. Not 2. 6. The physical planet itself is just over 2 Jupiter radii wide, but the cloud of escaping gas surrounding it is so vast and so dense that when viewed in the light of helium absorption, the planet appears to swell to nearly 6 times the width of Jupiter. The actual solid or liquid core, if one even exists inside this diffuse object, is surrounded by an envelope of gas that extends far beyond the planet's nominal surface, gradually thinning into a stream of material that feeds the star. This is not a stable planet with a thin atmosphere gently leaking at its edges. This is a planet whose outer layers are pouring into space in real time, forming structures visible across millions of kilometers, reshaping the planet's apparent size depending on which wavelength you observe it in. The distinction between the planet and its escaping atmosphere has become almost meaningless. Where does the planet end and the outflow begin? The boundary is not sharp. It is a gradient, a smooth transition from bound gas to unbound stream to stellar wind. The combined picture that emerges from these observations is one of a world in extremis. A planet that is simultaneously one of the largest by radius and one of the most insubstantial by mass. A world whose atmosphere is escaping at a rate that will strip it bare within cosmic timescales that are startlingly short. A planet whose host star is evolving in real time, brightening and swelling, tightening the noose of radiation around an already fragile companion. And this picture raises a question that goes beyond Hat P, 67b itself. If planets in this density regime are supposed to lose their atmospheres within 100 million years, and Hat P67b has only recently entered this regime, then how many other planets have already crossed this threshold and vanished? How many worlds like this one existed in the past, briefly enormous and luminous and strange, before they evaporated into nothing or were swallowed by their dying stars? The rarity of objects in this corner of the mass-radius diagram is not just a curiosity, it is a census of destruction. We see so few planets here because most of them are already gone. What remains to be understood is how a planet gets this inflated in the first place. The mechanisms that pump energy into a close-orbiting gas giant, the physics that determines how deeply that energy penetrates, and the interplay between inflation, mass loss, and stellar evolution form a web of processes that astronomers are still untangling. What comes next takes us inside the planet itself, into the physics of what it means for a world to be inflated, and into the direct evidence that HAT P67b is not merely large, but actively coming apart at the seams. To understand how HAT P67b became what it is, you need to forget almost everything you know about how planets work. Not because the physics is different, the laws are the same everywhere, but because the environment this planet inhabits is so extreme that familiar physics produces unfamiliar results. A gas giant in the cold outer reaches of a planetary system is a stable, well-behaved object. A gas giant 10 million kilometers from a luminous subgiant star is something else entirely. It is a pressure cooker with the lid bolted on wrong, and the flame underneath is getting hotter by the century. Start with the basics. What determines how big a gas giant is? For a cold, isolated gas giant, the answer is straightforward. Its radius depends on two things. Its mass, meaning how much hydrogen, helium, and heavier elements it contains, and its age, meaning how long it has had to cool and contract since formation. Gas giants are born hot. The gravitational energy released during their formation heats the material to thousands of degrees. Over time, the planet radiates this heat into space and contracts. The interior cools, the pressure drops, the radius shrinks. Given enough time, a gas giant of a specific mass and composition settles into a predictable equilibrium radius, determined entirely by the balance between gravity squeezing inward and the pressure of degenerate electrons resisting compression. This cooling process is slow. It takes billions of years. Jupiter, at roughly 4.5 billion years old, has contracted to a radius of about 11.2 Earth radii, or just over 1 Jupiter radius by definition. Models predict that Jupiter was perhaps 30 to 40% larger when it first formed, and it will continue to shrink imperceptibly over the coming billions of years. For cold gas giants, the relationship between mass, age, and radius is clean and predictable. Give an astronomer the mass and age of a cold gas giant, and they can tell you its radius to within a few percent. Now change one variable. Move the planet close to its star. When a gas giant orbits within a few hundredths of an astronomical unit from a luminous star, the energy budget changes dramatically. The planet is no longer cooling freely into the cold vacuum of space. One entire hemisphere is being blasted with radiation intense enough to heat the atmosphere to temperatures exceeding 1,000 Kelvin. This incoming energy does not just warm the surface, it fundamentally alters the planet's thermal structure, and through a chain of physical processes that scientists have spent 2 decades trying to fully understand, it can inflate the planet's radius far beyond what its mass and age alone would predict. The key question, the one that has driven hundreds of papers and fueled countless conference debates, is deceptively simple. How does the stellar energy get from the atmosphere into the deep interior of the planet? Because that is what is required. Warming the outer atmosphere alone is not enough to inflate the radius significantly. The visible atmosphere of a gas giant represents a tiny fraction of its total mass. To swell the entire planet, energy must penetrate deep, down to pressures of hundreds or thousands of bars, where the bulk of the planetary material resides. Only by heating the deep interior can you reduce its density enough to expand the whole structure. If the atmosphere simply absorbed stellar radiation and re-radiated it back into space, the deep interior would remain cold, and the planet would maintain its equilibrium size. The atmosphere would be hot. The interior would be cool. The radius would be normal. But observations show that hot Jupiters are larger than this scenario predicts. Something is transporting energy from the irradiated atmosphere into the deep interior, and it is doing so efficiently enough to keep the planet puffed up over billions of years. Several mechanisms have been proposed to explain this energy transport. Each has strengths, each has limitations. And the current scientific consensus is that more than one may be operating simultaneously. with their relative contributions varying from planet to planet depending on mass, temperature, orbital parameters, and magnetic field strength. The first and most widely discussed mechanism is ohmic dissipation. The concept works like this. The intense stellar irradiation heats the atmosphere of a close-in gas giant to temperatures where alkali metals like sodium and potassium become thermally ionized. This creates a partially ionized atmosphere that can conduct electricity. Powerful atmospheric winds, driven by the enormous temperature difference between the scorching day side and the cooler night side, blow this ionized gas across the planet's magnetic field lines. Moving a conductor through a magnetic field generates electrical currents. These currents flow through the deeper, more resistive layers of the atmosphere, where they dissipate as heat through ohmic resistance, the same process that makes a wire glow when you run electricity through it. The heat deposited by these currents warms the interior and slows the planet's gravitational contraction, keeping it inflated. Ohmic dissipation is appealing because it naturally links the degree of inflation to the level of stellar irradiation. Hotter atmospheres produce more ionization, which generates stronger currents, which deposits more heat in the interior. This matches the observed trend that more highly irradiated planets tend to be more inflated. Population-level studies by Thorngren and Fortney found that the functional form of the heating efficiency required to explain the observed radii most closely matches what the ohmic dissipation model predicts, including a decrease in efficiency at the very highest temperatures, where the atmosphere becomes so ionized that it becomes too conductive, short-circuiting the currents before they can penetrate deep enough to matter. However, ohmic dissipation has limitations. Some calculations suggest the total heating power available through this mechanism may not be sufficient to explain the most extreme inflation cases. Additionally, the depth at which ohmic currents deposit their energy is relatively shallow, near the radiative convective boundary rather than deep in the convective interior. A 2025 study found evidence that hot Jupiter inflation is primarily driven by shallow heating, with intrinsic luminosities from the deep interior reduced by 95 to 97%, relative to models that assume all heating occurs at the planet's center. This suggests ohmic dissipation or a similar shallow mechanism is the dominant process, but it also means that the energy is not penetrating as deeply as some earlier models assumed. The second mechanism is tidal heating. As a planet orbits close to its star on an orbit that is even slightly eccentric, meaning slightly elliptical rather than perfectly circular, the gravitational pull from the star varies over the course of each orbit. This varying pull flexes the planet's interior, generating friction and heat, the same process that drives the spectacular volcanism on Jupiter's moon Io. Tidal heating can deposit energy directly into the deep interior, making it more effective at inflating the planet than shallow mechanisms. But tidal heating requires orbital eccentricity, and most hot Jupiters on very short period orbits have had their eccentricities damped to nearly zero by the very tidal forces that would generate the heating. Tidal circularization typically occurs on timescales much shorter than the age of the system, meaning that by the time we observe these planets, there is little eccentricity left to drive significant heating. For HAT P67b specifically, the orbit appears to be very close to circular, limiting the role tidal heating can play in its current inflation. However, tidal interactions may have contributed earlier in the planet's history, when its orbit was still circularizing. The third mechanism involves the advection of potential temperature. This was proposed by researchers who modeled the atmospheric circulation of hot Jupiters and found that the powerful winds transporting heat from dayside to nightside do not simply redistribute thermal energy horizontally. Through the conservation of mass and momentum, these circulation patterns can force air downward into the deeper atmosphere on the night side, carrying entropy from the hot upper layers into the cooler interior. This process effectively attaches the deep atmosphere to a hotter adiabat than one-dimensional models predict, meaning the temperature at depth is higher than it would be without the circulation. A hotter interior is a more expanded interior, and the planet inflates. This mechanism is elegant because it requires nothing exotic. No magnetic fields, no tidal eccentricity, just the atmospheric circulation that any strongly irradiated planet would naturally develop. But modelling it accurately requires sophisticated three-dimensional general circulation models, and different modelling groups have reached different conclusions about how much inflation it can produce. The debate remains active. For HAT P67b, the inflation is extreme enough that a single mechanism may not be sufficient. The planet's mass of roughly 0.45 Jupiter masses places it squarely in the range that population studies have identified as most susceptible to inflation. Research has shown that planets between approximately 0.37 and 1 Jupiter mass inflate more dramatically in response to stellar irradiation than either lighter or heavier planets. Below this range, planets lack enough envelope mass to sustain large radii. Above this range, the increased gravitational self-compression of the more massive planet resists inflation more effectively. HAT P67b sits in the sweet spot where a relatively modest amount of additional internal heating can produce enormous increases in radius because the planet's own gravity is too weak to fight back. This is a crucial insight and one of the most counterintuitive aspects of planetary physics. Adding mass to a planet does not always make it bigger. Beyond a certain threshold, roughly in the range of a few Jupiter masses for cold planets, additional mass actually makes the planet smaller because the increased gravity compresses the existing material more than the new material adds volume. This means that the relationship between mass and radius for gas giants is not a simple upward curve. It is a curve that rises, peaks, and then turns over. The largest radii belong not to the most massive planets, but to the most inflated ones, planets with moderate masses subjected to extreme heating. HAT P67b represents the extreme end of this phenomenon. A planet with less than half of Jupiter's mass, inflated by intense stellar irradiation to more than twice Jupiter's radius. The ratio of its radius to what models predict for a cold planet of the same mass is staggering. A cold, isolated planet of 0.45 Jupiter masses should have a radius of roughly 1 Jupiter radius, or perhaps slightly less. HAT P67b is more than double that. Something has more than doubled the volume this planet should occupy, filling it with the same amount of gas spread across a space roughly 10 times larger. To grasp what this inflation does to the planet's interior, it helps to compare it directly with Jupiter's internal structure. Jupiter, despite being a gas giant, has a surprisingly well-organized interior. Beneath the visible cloud tops, atmospheric pressure climbs rapidly with depth. Within a few thousand kilometers, hydrogen gas transitions from a molecular gas to a liquid. Deeper still, at pressures exceeding roughly 2 million atmospheres, hydrogen undergoes a phase transition into metallic hydrogen, a state where the electrons are stripped from their atoms and flow freely like electrons in a metal. This metallic hydrogen layer extends for tens of thousands of kilometers and is responsible for generating Jupiter's powerful magnetic field. At the very center sits a core of heavier elements, rock and ice compressed to extraordinary densities, possibly 10 to 20 times the density of water. The pressure at Jupiter's center reaches roughly 40 million atmospheres. The temperature exceeds 20,000 Kelvin. Now imagine spreading Jupiter's mass, or rather less than half of it, across a volume 10 times larger. The entire pressure profile collapses. Every layer thins out. The molecular to metallic hydrogen transition, which depends on extreme pressure, may occur much deeper relative to the planet's radius, or may be greatly diminished in extent. The core, if one exists, would sit at the center of a vastly more diffuse envelope, its gravitational influence diluted across an enormous volume. The pressure gradient from surface to center would be far gentler than Jupiter's. Instead of a sharply layered structure with distinct phase boundaries, HAT P67b likely has a gradual, almost featureless interior profile, density increasing slowly inward from the near vacuum of its bloated outer atmosphere toward whatever modest concentration of heavier elements persists at its center. There are no dramatic phase transitions, no crushing metallic hydrogen shell, no searing high-pressure core rivaling the conditions inside a star. Just a smooth, gentle gradient from something to nearly nothing, spread across a diameter larger than any planet in our solar system by a factor of more than 2. This structural comparison highlights something the density number alone cannot convey. Jupiter is dense because its material is squeezed. HAT P67b is diffuse because its material is stretched. They are made of roughly the same ingredients, hydrogen and helium with traces of heavier elements, but one is compressed by its own immense gravity into a tightly layered structure. The other is inflated by external energy into something closer to a vast, warm, tenuous cloud. The result is a density that barely qualifies as material in any conventional sense. 0.061 grams per cubic centimeter. To put this in terrestrial terms, this is about 1/16th the density of water. It is roughly 1/22nd the density of Jupiter. If you could somehow place HAT P67b in a cosmic bathtub large enough to hold it, it would float so high that barely any of the planet would be submerged. The mental image fails entirely because at this density, the planet does not behave like a solid or even a liquid. It is a gaseous envelope, a diffuse cloud of hydrogen and helium with no defined surface, thinning gradually from a denser core region into the near vacuum of space. And that is the crux of the strangeness. When does a planet stop being a planet and start being a cloud? For a world like Jupiter, the distinction is clear. The density increases rapidly with depth, from the thin outer atmosphere to the fluid metallic hydrogen interior to a dense core of heavier elements. There is structure, layering, a clear sense that material is being held together by immense gravitational pressure. For HAT P67b, the gradient is far gentler. The material is spread so thinly across such an enormous volume that the boundary between planet and space becomes a matter of definition rather than physical reality. It is worth pausing here to appreciate how rare HAT P67b truly is, even among the already rare class of inflated hot giants. The Wang et al. 2025 study notes that it is one of only 4 confirmed planets to cross below the density boundary of 0.1 grams per cubic centimeter. The exact membership of this group shifts as measurements are refined, but the shared characteristics are unmistakable. All occupy orbits tighter than a week. All receive extreme irradiation from their host stars. All are thought to be on unstable evolutionary paths that will end in atmospheric destruction within cosmically brief timescales. But even within this exclusive group, HAT P67b stands apart. Its density of 0.061 grams per cubic centimeter is significantly lower than most of its nearest peers, and its mass, less than half a Jupiter, is the lowest of the bunch. The others at least have the excuse of being closer to Jupiter's mass. HAT P67b achieves its absurd radius with even less raw material, making the inflation proportionally more extreme and more difficult for any single theoretical mechanism to explain. It is not merely a member of the inflated planet club, it is the member that makes the other members look ordinary. This diffuseness is not merely an abstract concern, it has direct physical consequences. A less dense planet has weaker surface gravity, which means its atmosphere extends to higher altitudes relative to the planet's radius. The scale height, the vertical distance over which atmospheric pressure decreases by a factor of roughly 2.7, is proportional to temperature and inversely proportional to surface gravity. For HAT P67b, the combination of high atmospheric temperature and low surface gravity produces a scale height of approximately 800 kilometers. For comparison, Earth's atmospheric scale height is about 8.5 kilometers. HAT P67b's atmospheric scale height is roughly 100 times larger than Earth's in absolute terms, and about 4 times larger even when measured as a fraction of the planet's own radius. This enormous scale height is precisely what makes the planet such an extraordinary target for atmospheric characterization. In transmission spectroscopy, the strength of atmospheric absorption features depends on the ratio of the atmosphere's annular cross-section to the stellar disk. A puffier atmosphere with a larger scale height produces deeper, more easily detectable absorption signatures. This is why multiple research teams have been able to detect a wealth of atmospheric species and escape signatures from HAT P67b, despite its host star's distance of 1200 light-years. The planet's atmosphere is so extended that it stamps a conspicuous fingerprint on every beam of starlight that passes through it. But the same puffiness that makes the planet scientifically accessible also makes it structurally vulnerable. And this is where the story shifts from inflation to destruction. A planet's Roche lobe is the region of space within which material is gravitationally bound to the planet. Outside this boundary, material falls under the gravitational influence of the host star and escapes. The size of the Roche lobe depends on the ratio of the planet's mass to the star's mass and on the orbital separation. For HAT P67b, the combination of its low mass, its massive host star, and its tiny orbital distance produces a Roche lobe that is remarkably small relative to the planet's inflated radius. The planet fills, and in fact overfills, its Roche lobe. Its distended atmosphere extends beyond the gravitational boundary, where material can remain bound to the planet. The gas that crosses this boundary does not hover uncertainly at the edge. It streams outward, falling toward the star along ballistic trajectories shaped by the combined gravitational fields of the planet and the star, plus the Coriolis forces arising from the orbital motion. To visualize this, imagine a water balloon being squeezed through a narrow opening. The Roche lobe defines the shape of that opening, a teardrop-shaped gravitational boundary with its narrowest point, called the first Lagrange point, aimed directly at the host star. Gas at the top of the planet's atmosphere, heated and expanded beyond this point, spills through the narrow neck of the gravitational funnel. But unlike water pouring from a balloon in a straight line, this gas is moving in a rotating reference frame. The planet is orbiting the star at tens of kilometers per second. The escaping gas retains most of this orbital velocity. As the gas leaves the planet and enters the star's dominant gravitational field, the Coriolis effect curves its trajectory. Gas launched from the day side, which faces the star, gets swept forward along the orbit by the orbital motion, creating a stream of material that races ahead of the planet like the bow wave of a ship. Gas escaping from the trailing hemisphere follows a different path, curving backward into a fainter tail. The leading stream is brighter and denser, because dayside irradiation drives the strongest outflow from the hemisphere closest to the star. The result is a planet wrapped in a lopsided shroud of escaping gas, with a prominent leading arm extending far ahead of its orbital position and a dimmer trailing tail stretching behind. This asymmetric structure is precisely what the helium triplet observations revealed. The excess absorption detected before the transit itself is the signature of the leading arm passing in front of the stellar disk before the planet's physical body has arrived. This is the mechanism behind the leading helium tail we have already seen in the observations. The visualization makes concrete what the observations already confirmed. The gas is not drifting aimlessly. It is being sculpted by orbital dynamics into a coherent stream, a structure with a definable shape and velocity, extending far ahead of the planet and revealing the anatomy of a world in the process of unraveling. The mass loss rate, consistent with the estimates derived from the helium observations, is on the order of 10 million metric tons per second. To grasp what that means at longer timescales, consider that in a single Earth day, the planet sheds roughly 800,000 billion kilograms of atmosphere. Over a full year, the cumulative loss exceeds the mass of every building, vehicle, ship, and structure humanity has ever constructed, combined many times over. The hemorrhage is relentless at every timescale you choose to examine it. The scale of this loss sounds catastrophic, and it is, but perspective matters. HAT P67b has a total mass of approximately 0.45 Jupiter masses, or about 8.5 times 10 to the 29th grams. At the current mass loss rate, it would take roughly 2.7 billion years to lose the entire mass of the planet. Since the runaway mass loss has only recently begun, driven by the host star's recent brightening as it evolves off the main sequence, the planet is not going to evaporate entirely before other processes intervene. The host star itself is expanding. Within 150 to 500 million years, the star will swell enough to either tidally disrupt the planet by stretching it beyond its structural limits or physically engulf it, swallowing the planet entirely as the stellar surface expands past the planet's orbit. The planet's fate is therefore sealed from two directions simultaneously. It is losing its atmosphere from above as stellar radiation drives the escape, and it is about to be consumed from below as the dying star expands toward it. Whether the atmosphere strips away first or the star swallows the planet first depends on uncertain details of the stellar evolution and the mass loss rate, but the outcome is the same. Within a few 100 million years, HAT P67b will cease to exist as a recognizable planet. The spectroscopic detections we explored previously now acquire a deeper physical meaning in the context of Roche lobe overflow. The sodium and ionized calcium found by the Carmenes team are not simply atmospheric constituents drifting at high altitudes. They are tracers of an atmosphere being heated to temperatures far above what radiative equilibrium alone would produce. The ionized calcium in particular demands explanation, because creating that species requires temperatures typically associated with much hotter planets. The most likely source of the additional energy is the escaping outflow itself. As gas accelerates through and beyond the sonic point, the conversion of thermal energy to kinetic energy and the absorption of extreme ultraviolet photons create a thermosphere heated to approximately 9,900 Kelvin, nearly 5 times the planet's equilibrium temperature. This superheated layer is not a static shell. It is the launch pad for a transonic planetary wind. The physics of this wind is the same physics that drives the solar wind from our own sun. The sun's corona, heated to millions of degrees by mechanisms still debated, expands outward, accelerates through the speed of sound, and streams into interplanetary space. HAT P67b's upper atmosphere does the same, except the wind flows from a planet rather than a star. Gas in the lower thermosphere moves slowly, pushed upward by the pressure of the superheated layer below. As it rises and the pressure drops, it accelerates through the sonic point and continues gaining speed as it expands into the near vacuum beyond the Roche lobe. The material then joins the leading and trailing streams we have already traced, adding to a continuously replenished structure that reshapes the planet's apparent size depending on the wavelength of observation. This wavelength dependence is one of the most striking consequences of the outflow. In broadband visible light, the planet's transit reveals a disk of approximately 2.14 Jupiter radii. That is the radius of the opaque photosphere, the depth at which the atmosphere becomes thick enough to block a measurable fraction of starlight. But in the narrow spectral window of the helium triplet, the transit tells a different story. The absorption begins before the planet's disk crosses the stellar limb, produced by the leading tail passing in front of the star ahead of the planet itself. It continues after the disk has exited, produced by the trailing tail following behind. The effective radius in helium light reaches approximately 6 Jupiter radii, nearly 3 times the broadband radius. The planet you see depends entirely on how you look at it. In white light, it is a very large planet. In helium light, it is a monstrous cloud with a planet hiding somewhere inside. All of these observations converge on a single, consistent picture. HAT P67b is not merely a large planet. It is not merely an inflated planet. It is a planet in a state of active disassembly. Its atmosphere is pouring into space at millions of tons per second. Its effective size depends on which wavelength you choose to observe it. Its Roche lobe is overfilled, Its host star is brightening and expanding toward it. Its density is so low that the word planet struggles to contain what it is, and yet this object exists. It is real. It has been observed by multiple independent teams using multiple instruments at multiple wavelengths. Its mass, radius, density, atmospheric composition, mass loss rate, tail structure, and orbital parameters are all measured and documented in the peer-reviewed literature. It is not a theoretical curiosity or a simulation artifact. It is a confirmed world, catalogued in the NASA Exoplanet Archive, listed among the largest radius planets known. The question is no longer how big a planet can get. The question is what the word planet means when the object in question is less dense than a marshmallow, actively hemorrhaging its own atmosphere into a leading tail 130 times its own width and destined to be consumed by its dying star within a few 100 million years. That question, the philosophical aftermath of everything we have just measured, is where this story ends. What comes next confronts the deepest implication of all. Not what HAT P67b is, but what its existence means for the concept of a planet, for the fragility of cosmic structures, and for the terrifying possibility that the largest things in the universe are not the strongest but the most temporary. There is a moment in every great scientific story when the facts stop being facts and start being something else. Something that changes how you see the world, not because the data shifts, but because your understanding of what the data means finally catches up to what the data has been saying all along. This is that moment. Because the terrifying thing about HAT P67b is not its size, it is not the helium tail, it is not the mass loss rate, or the dying star, or the density lower than a marshmallow. The terrifying thing is what all of these measurements, taken together, do to the concept of a planet itself. We need to confront the title of this story directly. Meet the largest planet in the universe. Is that true? Is HAT P67b the largest planet in the universe? The honest answer is layered, and the layers matter. Here is what we can say with confidence. HAT P67b is one of the largest radius exoplanets confirmed to date. The NASA Exoplanet Archive, which serves as the most authoritative catalogue of confirmed exoplanets and their measured properties, lists its radius at approximately 2.14 Jupiter radii. Among the more than 5,700 confirmed exoplanets with measured radii, this places it at or very near the top of the distribution. The 2025 study by Wang and collaborators refers to it explicitly as the largest known hot giant planet. In terms of physical width, this is among the biggest planets humanity has ever confirmed, but calling it the largest planet in the universe requires caveats that honest science demands we state clearly. First, we have confirmed only a tiny fraction of the planets that exist. Our galaxy alone likely contains hundreds of billions of planets, and the observable universe contains roughly 2 trillion galaxies. The sample of 5,700 confirmed exoplanets represents an infinitesimal sliver of what is out there. Somewhere in the cosmos, there may be an even larger planet we have not yet detected. Claiming any specific object is the absolute largest in the universe is a statement about our catalogue, not about nature. Second, radius measurements for exoplanets carry uncertainties that grow with distance and depend on how well we understand the host star. HAT P67b's radius is measured relative to its host star's radius. If the stellar radius is revised upward or downward, the planetary radius moves with it. The current measurement is robust, but science is a process of continuous refinement. Future observations could adjust the number. Third, the boundary between a planet and a brown dwarf is not perfectly sharp. Brown dwarfs are objects too massive to be planets but too small to sustain stable hydrogen fusion like true stars. The conventional dividing line is placed at roughly 13 Jupiter masses, the threshold above which deuterium fusion can occur. But some objects near this boundary have radii comparable to, or even larger than HAT P67b, depending on their age and temperature. Whether those objects count as planets or as failed stars is partly a matter of definition. If you include young, hot brown dwarfs in the comparison, the radius record becomes murkier. What we can say without qualification is this. Among confirmed objects that are unambiguously planetary in mass, HAT P67b has one of the largest radii ever measured, and it achieves that radius not through brute accumulation of material, not through being the most massive or the most gravitationally powerful, but through being inflated to a degree that pushes the concept of a planet to its structural limit. This is the real story. Not a record, a revelation. Think about what the word planet means to most people. It means a world, a place, something with a surface, or at least a definable boundary, something with substance. When you say the word planet, you conjure an image of a thing, a discrete object with an inside and an outside, a place where something could hypothetically stand, or float, or orbit. Even gas giants, which lack solid surfaces, feel like places in our imagination. Jupiter has bands, Saturn has rings, Neptune has storms. They have structure, character, identity. They feel solid in the metaphorical sense, even when they are not solid in the physical sense. HAT P67b dismantles this intuition, not gradually, completely. Consider what this object actually is when you strip away the language of planetary science and describe it in plain physical terms. It is a concentration of hydrogen and helium gas, less massive than Jupiter, spread across a volume roughly 10 times larger than Jupiter occupies. Its density is so low that the gas at its nominal surface, to the extent that the concept of a surface applies at all, is thinner than the gas inside many laboratory vacuum chambers on Earth. It has no defined edge. Its atmosphere does not end at a boundary. It thins continuously outward, merging seamlessly into the stream of escaping gas that extends 130 planetary radii ahead of it in its orbit. At certain wavelengths, the planet appears to be 6 times the width of Jupiter, because the escaping gas cloud absorbs starlight far beyond where the gravitationally bound atmosphere ends. Where is the planet in all of this? Where does the object stop and the process begin? These are not rhetorical questions. They are genuine physical ambiguities that HAT P67b forces us to confront. For a rocky planet like Earth, the answer is obvious. The surface is the boundary. For Jupiter, the answer is less obvious but still manageable. The visible cloud tops serve as a reasonable proxy for the planet's edge, even though the atmosphere extends above them. For HAT P67b, the answer dissolves. The planet is a diffuse concentration within a larger diffuse outflow. It is a dense region within a less dense stream within the near vacuum of space. It is not a thing so much as a gradient. This might sound like philosophical hand-wringing, but it has concrete scientific consequences. When astronomers measure the radius of a transiting exoplanet, they measure the radius at which the planet's atmosphere becomes opaque enough to block a detectable fraction of starlight. For a compact planet, this radius closely corresponds to the physical edge of the object. For HAT P67b, this radius captures the outer boundary of a vastly extended atmosphere that may or may not be gravitationally bound to the planet. The number we call the radius is not the edge of a world. It is the edge of a visibility threshold. The planet extends far beyond it in some physical sense, while also being far smaller than it in another physical sense. If by planet, you mean only the gravitationally bound material with significant density, this ambiguity extends to the mass measurement as well. When we say the planet has a mass of 0.45 Jupiter masses, we mean the total gravitational influence of the object as inferred from its effect on the host star. But that mass includes material currently in the process of escaping. The planet's mass is not a fixed quantity. It is decreasing in real time at a rate of roughly 10 million metric tons per second. The mass we measure today is not the mass that existed 1 million years ago, and it is not the mass that will exist 1 million years from now. The planet is a snapshot of a process, not a stable object. This is deeply strange. We are accustomed to thinking of planets as permanent fixtures of their stellar systems. Earth has been here for 4.5 billion years. Jupiter has been here just as long. The planets of our solar system feel eternal on any human timescale, and even on most astronomical timescales they are stable. They will outlast our Sun's main sequence lifetime. They will persist, in some form, long after the Sun becomes a white dwarf. HAT-P67b will not persist. Its existence as a recognizable planet is temporary. Not temporary on the scale of the universe's lifetime, temporary on the scale of stellar evolution. Within 150 to 500 million years, the planet will either lose its atmosphere entirely through the ongoing escape process or be engulfed by its host star as the star swells into its red giant phase. Either way, the object we currently call HAT-P67b will cease to exist within a time frame that is short compared to the age of the system itself, which is already more than 1 billion years old. The planet has lived most of its life in a state of precarious stability. For over 1 billion years it was inflated but intact. Its atmosphere was heated and extended but not escaping at catastrophic rates. The host star, during its main sequence lifetime, did not irradiate the planet with enough extreme ultraviolet radiation to drive runaway mass loss. The planet existed in a kind of metastable state, like a balloon inflated to an uncomfortable size but not yet popping. Then the star evolved. As the hydrogen fuel in its core depleted, the star began to restructure itself, brightening and expanding as it transitioned from the main sequence to the subgiant branch. The increased luminosity changed the irradiation environment around the planet. The extreme ultraviolet flux climbed past the threshold needed to drive atmospheric escape at rates that exceed the planet's ability to maintain itself. The balloon started leaking, and unlike a balloon, it cannot be reinflated from below because the very energy source driving the inflation is also driving the destruction. This creates a paradox that lies at the heart of what makes HAT-P67b so scientifically fascinating. The same stellar proximity that inflates the planet to one of the largest radii ever measured is also what is killing it. The planet is enormous because of the star. The planet is dying because of the star. Its defining characteristic, its extraordinary size, is also the signature of its destruction. There is a broader lesson here about the nature of extremes in the universe. The most extreme objects are often the most temporary. The most massive stars burn through their fuel in a few million years. The most luminous quasars represent brief periods of intense accretion onto supermassive black holes. The most energetic events, supernovae and gamma-ray bursts, last for seconds or weeks. Nature can produce extraordinary extremes, but it cannot sustain them. The cost of being extreme is brevity. HAT-P67b follows this pattern. It is extreme in radius. It is extreme in its ratio of size to mass. It is extreme in the extent of its atmospheric escape. And it is transient. The universe built a planet at the outer edge of what physics allows, and the price of occupying that edge is a lifespan measured in hundreds of millions of years rather than billions. Among the 5,700 confirmed exoplanets, objects as extreme as HAT-P67b are vanishingly rare, not because the conditions that create them are impossible, but because the conditions that create them also destroy them. We see so few planets in this corner of the mass radius diagram because they do not stay there long enough to be caught in significant numbers. This rarity carries an implication that is both scientifically important and emotionally striking. For every HAT-P67b we observe today, there may be dozens or hundreds of former planets that once occupied the same extreme territory and have since been destroyed, stripped of their atmospheres, consumed by their expanding stars, reduced to bare rocky cores or erased entirely. The mass radius diagram is not a static map. It is a snapshot of a population in constant flux, with objects entering the extreme inflation zone, persisting briefly, and then exiting through destruction. We are looking at the survivors, the ones that happen to still exist during the sliver of cosmic time in which human telescopes are operating. There is something almost mournful about this. The largest planet we have found is not a monument. It is a ruin in progress. It is not sitting at the top of a hierarchy, presiding over lesser worlds with gravitational authority. It is falling apart, bleeding into space, being consumed by the object that gave it its extraordinary size. The king is not on a throne. The king is on a pyre. But mourning is a human response. The universe does not mourn. The universe recycles. The gas escaping from HAT P67b does not vanish. It streams toward the host star, where some of it will be incorporated into the stellar envelope. Some will be swept away by the stellar wind into the interstellar medium. Over millions of years, this material will disperse into the broader galactic environment, mixing with the gas and dust from which future generations of stars and planets will form. The atoms that currently constitute HAT P67b, the hydrogen forged in the Big Bang, the helium produced in the first minutes of cosmic time, will go on to build new worlds around new stars in new planetary systems. The planet dies, the matter persists. The cycle continues. This perspective reveals something about the role of destruction in cosmic evolution. Planetary systems are not built once and preserved forever. They are dynamic environments where objects form, interact, migrate, collide, inflate, deflate, evaporate, and merge over timescales that dwarf human experience. The placid stability of our own solar system, where 8 planets have orbited in roughly the same configuration for 4.5 billion years, is not the universal norm. It is one outcome among many. Other systems are far more violent, far more dynamic, far more temporary. HAT P67b exists in one of these violent systems, a massive, rapidly rotating, evolving star, a close-orbiting, inflated, evaporating planet, a distant binary companion whose gravitational influence may have shaped the system's early architecture. This is not a system in equilibrium. It is a system in transition, moving from one state to another, and the planet is the most visible casualty of that transition. The scientific community continues to study HAT P67b precisely because of its extremity. Hubble Space Telescope observations are planned or in progress to characterize the atmospheric escape in greater detail. The helium tail offers a natural laboratory for studying hydrodynamic outflows from planetary atmospheres, a process that is thought to have shaped the demographics of the entire exoplanet population. The so-called radius valley, the observed gap in the size distribution of exoplanets between roughly 1.5 and 2 Earth radii, is believed to result from atmospheric escape stripping the envelopes of smaller planets, leaving behind bare rocky cores. HAT P67b represents the same process operating at a much larger scale, on a gas giant rather than a sub-Neptune, driven by the extreme environment of a close orbit around an evolving star. Understanding how HAT P67b loses its atmosphere informs models of atmospheric escape across all planetary masses and orbital configurations. The mass loss rate, the outflow temperature, the structure of the leading and trailing tails, the interaction with the stellar wind, these are all data points that constrain the physics of a process that has shaped the population of planets we observe throughout the galaxy. Every exoplanet survey that counts how many planets exist at each size and orbital period is implicitly counting the survivors of atmospheric escape. HAT P67b helps us understand who did not survive. The planet also challenges theoretical models of inflation itself. At a radius of more than 2 Jupiter radii and a mass below half a Jupiter mass, it occupies a regime where standard interior models require significant additional heating to reproduce the observed size. The exact combination of mechanisms operating in this planet, whether ohmic dissipation, advective transport, tidal effects, or something not yet identified, remains an active area of investigation. HAT P67b serves as an extreme test case. Any theory of hot Jupiter inflation must be able to produce a planet this large at this mass, without violating other observational constraints. If a model cannot reach 2.14 Jupiter radii at 0.45 Jupiter masses under the irradiation conditions of this system, the model is incomplete. And here we arrive at the deepest layer of the story, the one that sits beneath the measurements and the mechanisms and the models, the one that makes this more than a science report and turns it into something that changes how you see the night sky. When you look up at the stars tonight, you are looking at a universe that builds things beyond human imagination, not just larger versions of familiar objects, genuinely alien structures that obey the same laws of physics you learnt in school but produce outcomes you never would have predicted. A planet wider than 2 Jupiters, lighter than half a Jupiter, less dense than candy, actively hemorrhaging its own atmosphere into a spectral tail visible from 1,200 light-years away. An object so diffuse that the distinction between planet and surrounding space becomes a matter of convention rather than physical reality. A world that is not a world. A place that is not a place. A thing that is barely a thing, more process than object, more transition than permanence. This is what the universe does when you push physics to its edges. Not chaos, not randomness. Structure, but structure so extreme it defies the categories we invented to describe it. HAT P67b is a planet by definition. It orbits a star. It has a measurable mass below the deuterium fusion threshold. It transits. It has an atmosphere. It checks every box on the official checklist. But lived experience, the intuitive sense of what a planet should be, recoils at the description. This is not a world. This is a temporary concentration of gas masquerading as a world, an exaggeration drawn in hydrogen and helium, held together by just enough gravity to earn the name planet, and destined to lose even that fragile coherence within a few 100 million years. And yet, it is magnificent, not despite its fragility, but because of it. The universe did not have to build objects like this. The laws of physics permit stable, boring planets on stable, boring orbits around stable, boring stars. Most planets are exactly that. Ordinary, durable, unremarkable. But physics also permits the extraordinary. It permits objects that exist at the boundary of possibility, balanced between inflation and collapse, between coherence and disintegration, between being a planet and being a memory. HAT P67b exists at that boundary. For a brief window of cosmic time, it is one of the largest planets ever confirmed, a swollen monument to what happens when an ordinary amount of gas is subjected to extraordinary conditions. And then, within a time frame shorter than the age of the oldest fossils on Earth, it will be gone. The largest planet is not the most powerful. It is not the most massive. It is not the most gravitationally fearsome. It is one of the most fragile objects that has ever been called a planet. And that is the deepest terror this story has to offer. Not that the universe is large. You already knew that. Not that the universe is strange. You suspected that. But that the largest things the universe can build are sometimes the most delicate. That size and strength are not the same. That something can be enormous and insubstantial simultaneously. That the word planet, which you have used your entire life to mean something solid and enduring, can also describe a temporary cloud of gas thinner than a whisper, bleeding into the dark around a dying star, 1,200 light-years from everything you have ever known. The next time someone tells you about the largest planet in the universe, you will know the truth. It is not a titan. It is not a fortress. It is a ghost in the shape of a world, vast and hollow and vanishing. And the fact that it exists at all, even briefly, even temporarily, even now, is one of the most extraordinary things the universe has ever done.